afternoon. It's afternoon in Pittsburgh right now. So I don't know what's time in Germany right now.
Yeah, but this is also watched by everyone in the world, so doesn't matter.
Okay.
Yeah.
Yeah, sure. I'm Lee Zhang. I'm a PhD student at the University of Pittsburgh, and with advised by Dr. Kevin Ashley, we have been investigating both the potential of the and also the limitations of large language models in the legal reasoning. And also, like most members in from my group, obtained a law degree before this PhD program. So. Um, we are witnessing a transformation in the legal tech with the rise of the foundation models. They are reaching out to the a lot of subfields in the legal domain, such as the contract review. And we have seen that a lot of government websites providing the chatbot to provide the consulting to the lay people. And also in the field of litigation, we have seen a lot of people using the like ChatGPT and DeepSeek to organize their legal arguments. And these systems offer tremendous promises, but like from all these subfields, but they also present significant drawbacks. So, like in 2023, we saw a very hard lesson. One of these risks here, when a lawyer submitted a brief to a federal court with case citation that simply does not exist. When questioned, he admitted that he was using ChatGPT, which had hallucinated this non-existent precedents. More recently, in 2025, just a couple of months ago, three lawyers were sanctioned for citing the AI-generated fake cases in court documents. So it raises a critical question that drives our research. How can we harness these powerful AI systems, enhancing persuasion while mitigating manipulation?
Oh,
So
wow.
we are building, yeah, yeah, it's very interesting.
Mm.
Um, we are building on like the foundation work from Dr. Kevin Ashley's 1988 research. Our research journey led us to focus on three critical like challenges and standing in the way of reliable legal AI. Like firstly, hallucination. We the models invent factors for our legal precedents. And secondly, inadequate abstention, where models generate arguments even when they have no factor basis to do so. And thirdly, poor factor utilization, where models fail to use the specific facts of this case correctly. Our work involved from testing the basic capability to designing a like comprehensive system to tackle these very problems. So I will walk you through all these definitions and concepts here. Firstly, the task definition here is that we use the large language models to generate the three-play legal arguments. In this task, we represent the cases with a standardized set of 26 legal factors in the domain of United States trade secret law. Specifically, it's trade secret misappropriation law. For instance, KFC could claim misappropriation if an employee disclosed their secret receipt, which is a blend of herbs and spices, by publishing it in a cookbook. So the plaintiff here is the KFC, the owner of the trade secret, and the defendant is the employee who disclosed the receipt, who disclosed the receipt. The large language model is given a current case and two precedent cases. Um, the trade secret one and trade secret two, all represented by their legal factors. The argument scheme unfolds like this. The plaintiff argues for their position by citing a precedent case, the trade secret, which is in red circle here, that has shared the favorable factors with the current case. which is F4 and F6 here, and the defendant's response by distinguishing the plaintiff's cited case and presenting a different precedent as a counterexample that favors their side. And then the plaintiff is going to rebuttal. The plaintiff concludes by distinguishing the counterexamples presented by the defendant, pointing out the difference between these two cases and reinforcing the original statements. So our pilot study has identified threefold of the interconnected challenges that undermine the reliability of large language models in legal arguments: hallucination, inadequate abstention, and poor factor utilization. A failure in one area will exacerbate the others. For example, when a model is forced to generate an argument without a solid factor basis, it is far more likely to hallucinate facts to complete the task. So we set the test scenario here. To evaluate our models and methods, we designed 3 distinct legal scenarios to test the argument generation capabilities, their robustness, and their ethical behavior. Firstly is the arguable scenario. This is a standard scenario. The current case has a factual overlap with both the precedent cases. There are clear grounds for both sides to build an legal argument. What it tests here, this measures the system's core competence in legal reasoning, its ability to effectively use the provided facts to construct a coherent and persuasive argument when it is appropriate to do so. And the second scenario is a mismatched scenario. It is a trick one because the precedents provided are logically flawed for this task. For example, the case is intended to support the plaintiff actually as an outcome that favors the defendants. We want to use this scenario to test the system's integrity. It is an ethical and a reliable system should identify the contradiction and abstain from making an legal argument, rather than trying to force a deceptive point. And the last scenario is non-arguable one. In this scenario, there's no factual connection, which there are no shared factors between each case pairs. There is simply no evidence to build a legal argument. So this directly evaluates the system's capability to stay grounded in the provided facts and avoid hallucination. A successful outcome for this system is to abstain, recognizing and admitting that it cannot invent a connection that does not exist. This is a crucial safeguard against generating manipulative arguments. So the hallucination problem is particularly concerning. Models frequently invent factors that are not present in cases or misattribute factors between cases. In our previous analysis, this leads to arguments that appear coherent but built on a foundation of falsehoods, rendering them manipulative and untrustworthy. So this shows a screenshot comparing a correct output that only references factors actually present in cases versus a hallucinated output that invents non-existent factors. So the second matrix is the factor utilization, and the third is abstention. The equally problematic is the failure to abstain. A reliable system must know when not to make an argument. When a case lacks a factual basis for a claim, the system should refuse to generate an argument. However, many models proceed anyway, often by poorly utilizing the given facts or inventing new ones. So this limitations made it clear and simply using one single general purpose large language model is insufficient for the high stakes domain such as law or finance. We need a new approach that could explicitly target these weaknesses. This led us to develop this new reflective multi-agent framework, which I will describe. So this is the for the most straightforward approach. A single large language model is given an input and the basic prompt. The large language model generates the entire 3 legal arguments for the plaintiff, defendant, and plaintiff rebuttal in one continuous pass. The final text is produced without any intermediate steps for review or refinements. And the second approach we used here as a baseline is the linear. We inject a new paragraph into the prompt to explicitly hint the model to be cautious about the hallucination problem, and also to abstain if there's no overlap between the factors. So this prompt contains more specific instructions. The control is front-loaded into the instructions, relying on the model's capability to follow complex the directions. And the third one is the vanilla multi-agent. We provided 2 agents here, models here to play the role of plaintiff and defendant. And the key difference here is the sequential and interactive nature of the generation process. The output from one agent becomes part of the input for the next, simulating real-world basic debate. So our proposed method is using the agent here. We use a reflective multi-agent framework. Instead of the one single model, we use a team of specialized agents. And argument developers generate the initial arguments. Then it will decide which agent it will pass on to execute the following tasks, such as the factor analyze and the argument polisher. The entire process is applied to generate the 3 legal arguments, the plaintiff, the defendant, and the plaintiff rebuttal. This is the most complex deliberate information flow here, and also is kind of optional for it is all decided by the agent, by the argument developer agent itself. So for each play, an initial agent will produce the first draft of the agent for the current play, and then the draft could be passed to the factor analyst agent. The agent will use the tool provided with it to analyze whether it has a ground truth, whether it has a hallucination in the argument, and then it will give the feedback to the argument developer. And another agent used here is the polisher, the argument polisher. It will give feedback to the whether it use the most of the factors in the cases. So the polished argument becomes the final output for each play. To measure our system with factors, we compare it against the 3 baselines mentioned previously. The result for the successful obtention were dramatic. Our reflective multi-agent system vastly outperformed all the baselines here. For instance, with one model, our system successfully obtained in over 92 of the mismatched cases where it was the correct action. The baseline model almost never obtained, generating the flawed arguments instead. This showed the critical role of the 2 agents and the tool used in preventing the system from making unsupportable claims. And we provided error analysis, and also you can check it out in our paper. And our system also showed a significant improvement in factor accuracy and evidence utilization. In the most challenging non-arguable cases, our reflective framework cut down the hallucinated facts, improving the accuracy by a large margin over all these baselines. Furthermore, it also increased the factor utilization ratio, which leading to a more comprehensive and more well-grounded arguments. and also provided an error analysis here. So our research journey has yielded several important insights. Firstly, structured multi-agent fruit selection is a powerful method for mitigating critical large model weaknesses like hallucination and failure to understand. Secondly, specialized agent roles like our factor analyst provided a computable method for enforcing the factual grounding and ethical behavior. And thirdly, a system that knows when not to speak is fundamentally more trustworthy, especially in high stakes domain like law. I think that's all. Yep. Thank you.
Yeah, thanks a lot for the great contribution and great presentation. So maybe we delay the discussion, like involve discussion to the later part of the session, and we first move on to Aditya's talk.
Sure, I'll start sharing.
We have a discussion session afterwards. Okay.
Yes. Let me share my screen.
Yes, that would be great.
Is it visible?
Yes.
Okay, just give me a minute.
So yes, we have Aditya from CMU talking about OpenHands Versa, coding agent with multimodal browsing are generalist problem solvers. So look forward to your talk.
Yes. Hi everyone. My name is Aditya. I am currently a master's student in the Language Technologies Institute at CMU, and I will be presenting this work on OpenHands Versa. Let me adjust this a bit more. Yeah. So, like, the first question that I generally ask when I look at agent papers is that, like, why do you need another agent? So, like, we already have specialist agents already for like many popular use cases. So, some of the most popular use cases for agents are like software engineering, web browsing, and deep research. So, for software engineering, you have SWE agent, OpenHands. You have for browsing, you have browser use, browser gym. And for deep research, you have like Owl, Magentic one from Microsoft, Open Deep Research from Hugging Face. And like all of these are available for like open source. So you can like tweak these systems for your particular specific use case in each of these domains. Now, like one of the problems which all of these specialist agent systems suffer from is that they have mutually exclusive capabilities. And what I mean by that is that like coding agents cannot typically browse the web or like process multimodal file content. On the other hand, browsing agents are generally designed specifically for browsing and do not have any coding abilities or like using search APIs. And all of these systems are generally single agent systems. Deep research systems, on the other hand, have been like the most like powerful deep research systems have been multi-agentic. If you observe recently, they are they have a bit broader set of capabilities where they can browse, search the web, and process multimodal files, but their coding is very limited. So, like software engineering is not just about creating standalone Python programs, but actually dealing with large-scale repositories and being like having abilities like using a file, like interacting with a file system, using a bash terminal, editing files, debugging code. So all of these deep research systems are very limited in that aspect, and they all they can do is like do Jupyter notebook style coding or like just like writing standalone Python codes for like mini calculations or like some very simple use cases. So they generally don't work well for like other programming languages or for um let's say like software engineering like tasks like that we have in SWE bench. So like this raises a natural question that like do users need to interact with a broad variety of specialist agents for different use cases? So like or can we actually have a unified system that works like like which achieves competitive performance across diverse domains and like removes this need? So like that brings us to like the core research question that like what capabilities do we need to design a versatile agent? So like our observation is that like most real world tasks can be solved with like three capabilities: software engineering, browsing, and information access. So by information access, it means like searching the web and processing multimodal file content. Now there can be more specialized use cases where like you want more of these capabilities, but currently like in the span of like most recent agent benchmarks, these three capabilities broadly cover most of the benchmarks that you can think about. So SweBench, Web Arena, Gaia, Agent Company, OS Arena, all of these like actually require these three capabilities. So our idea is very simple. We take a strong coding agent, like OpenHands is a very strong software engineering agent, and integrate all of these capabilities into that agent to make it more versatile. So that's the high level idea. So like OpenHands is primarily a software development agent where it has a file editor or a file ACI through which it interacts with a repository. It has a code execution like system where like it uses a sandboxed environment where it can interact with an operating system through a bash terminal, and it has a very simple text-based browser. Now, creating a more versatile version of OpenHands uh, basically involves extending its capabilities at the first step. So what we do is like we inherit the coding abilities from OpenHands. So we do not really change that aspect of OpenHands because like it already works pretty well. What we do is like we change the like improve our browsing capabilities and make it multimodal browsing. So what we do is like multimodal browsing, the capability is basically browse web pages, perform interactive actions on pages like clicking on elements, typing into text boxes, scrolling through the web page. And this process is inherently multimodal. So you need to process both vision and text modalities from web pages. So what we do is that we take the screenshot of the viewport from the web page, and we provide like the accessibility tree of the web page as like multimodal context, as opposed to just providing the accessibility tree. So this also brings in a cost factor. So if you think about an agent in a multi-turn setting, if it interacts over multiple steps with a browser, it has multiple browsing observations. So do you actually show screenshots from previous steps as well? Because processing screenshots in LLMs is actually a very expensive task. So what we do is that we like truncate all the previous browsing observations and show just the observation from the most recent step. This significantly reduces the cost of like using this agent for browsing, and like it also like saves a lot of tokens in our context window. um and the third thing is like information access. So like typically, if you think about it, you can search information on the web using a browser as well. But the biggest challenge we face is that search engines typically block us using captchas or other access restriction mechanisms. So OpenHands, for instance, cannot like search the web through Google. So what we do is we typically use like specialized search APIs which are designed for agents, and we provide that as a tool to OpenHands Versa. And the second thing we do is like OpenHands cannot read multimodal file content. So let's say you have some PDFs or some audio files or spreadsheets and you would like to analyze that. OpenHands typically does not have these capabilities built in, which means it has to write programs to actually do those. So we make it simpler by like enhancing the file viewer capabilities of OpenHands and like allowing it to process multimodal content from different file formats. So after integrating these capabilities, like the next step is like evaluating the agent. So how do you evaluate if your agent is versatile enough? So we like instead of taking a single benchmark or like focusing on a specific data set, we take three benchmarks which span across different domains. So we first take Gaia, which is like deep research, where you have to do information synthesis from like multimodal files or through the web and like answer factual questions. We take up Cbench multimodal. So like while improving the browsing and information accessibilities of OpenHands, it is also important to ensure that you don't really degrade the coding abilities. So that's why we take on Cbench multimodal, which is like software engineering but with multimodal processing. And what you need to do is like fix bugs in front end like JavaScript libraries. And um, so like unlike Python programming in Cbench, like this involves like changing files across multiple programming languages, processing images in the GitHub issue, like actually visually verifying whether your fix works or not, and so on. And the agent company is a benchmark that evaluates agents for in settings where they work as a digital worker or a digital colleague in a simulated software company. So what do you typically expect software engineers to do in such like companies? So fixing bugs in repos, browsing companies' internal websites and finding information like browsing through cloud to like check spreadsheets or doing HR style tasks. And like communicating with coworkers through Slack or like web-based chat platforms. So these are some of the like different like capabilities that all of these benchmarks cover. And if you take a union of capabilities required, you can pretty much understand that they are very diverse. So programming, web browsing, information access, multimodal processing, all of that is covered through the choice of our benchmarks. And the real challenge here is that like how can you make an identical agent infrastructure to achieve strong performance on each of these three benchmarks? So we don't really tune our agent, we don't change the prompts, we don't change the tools. We use the same agent, same model and evaluate it. And that actually reflects a real world setting where you don't really have a control over the user query, where like it can be of any domain and your system should actually work out pretty well. So, like, let's discuss a bit about results. Our choice of baselines for each of these benchmarks is very simple. We take their leaderboards and like take the top performing systems and benchmark it against open hands versa. And another thing we do is that we take open hands and also like use the same model which we use in open hands versa and compare two different agent infrastructures using the same model. So if you talk about Gaia, all of these like are multi-agent systems which use like expensive models like Owen, and we have a single agent system with a single model, and we achieve competitive or like slightly better performance than these multi-agent systems. Another thing to note is that like all of these baselines, they have actually very highly specialized tools for like specific benchmarks. So they have multiple search APIs. They use a specific tool just for searching research papers because that actually boosts performance on Gaia. So these are like you don't really want to overfit your system to a particular benchmark, which these systems do. And that's what our finding shows that like, do you really need to do like over engineer your systems for a particular domain? Talking about SWE-bench multimodal, we benchmark against like SWE agent and its variants and agentless light, which is a like multimodal variant of agentless and open hands. So when using the same model, we see that we can retain the performance of open hands in open hands versa without any significant like dips, and like we significantly outperform all previous baselines on this benchmark, which is pretty interesting because like our like the capabilities which we have is like inherited from open hands, and like theoretically if you think about it, if you add more capabilities or add more tools, there is a chance that the model gets confused and like just the performance is degraded, but that really doesn't happen. And finally, for the agent company, we what we do is we take a popular multi-agent system called Owl, which has very strong performance on Gaia validation set, but they do not benchmark on Gaia test set. And we actually evaluate on agent company and it performs very bad. So this agent is particularly designed for deep research. It has a browser, it has a search engine. But when we actually try to evaluate it on like real world tasks in a company, it performs very poorly. So, and on the other hand, like when using the same model, open hands versa like outperforms open hands, and like obviously with better models, you get better performance. So Claude Sonnet 4 like significantly outperforms Claude 3.7 Sonnet for this benchmark. And so that's pretty much it about the results. Now, like you might think that why does such a simple system generalize? So like what we do is we analyze the tool use frequencies of the agents like open hands and open hands versa on all of these three benchmarks, and actually try to study that like what is the agent actually doing for us. So what we find is that like open hands versa chooses tools that are like intuitively very well aligned with task requirements. So let's say for deep research style of tasks, you would expect that the agent would like browse the web, like process multimodal files and like use the search APIs. So that's pretty much most of what our tool calls are. Like it uses web search, it uses the browser, and like it reads files. And there are some standalone programs for like calculation based questions where like you read a paper and do some calculations. It rarely uses the like file ACI for like editing files or creating new files, and it uses the bash terminal in some cases because sometimes the websites block you by captchas, so you try to actually curl the web page content locally and like analyze it using Python programs. So that's another interesting use case of how like agents come up with unique ways of solving tasks. which otherwise like don't exist. You can't imagine like humans doing. For the agent company, both the agents have like largely similar tool use patterns, where like the agent like uses the browser because each of these tasks involve interaction with some company internal website. You use like file ACI for like software engineering tasks, and you never use web search because in agent company you deal with companies internal websites and you don't really have to do like search the open web. So the agent is smart enough to realize that okay, I don't really need to use web search in this task. For Swebench multimodal, like yeah, again the same observations. Like you mostly use the bash terminal and the file ACI because it's software engineering. So you debug your code, you try to execute tests and see what happens. You rarely use like execute standalone programs using a Jupyter notebook or like use web search to like search over the web. And like most interestingly, like OpenHands Versa uses a browser to actually visually verify its fixes. So this capability cannot be leveraged by OpenHands because it does not have a visual like context from the browser. What the agent actually does here is that it like after it has debugged its code, it like hosts a local HTTP server and like opens it in its browser to actually see whether it's like the front end fix is actually working or not. So that's a large part of what OpenHands Versa does, and this capability actually can be exploited better as we have more stronger like models with visual reasoning and multimodal processing. So that's why we believe that like OpenHands Versa has the ability to do better domain aware tool selection than OpenHands. And that's pretty much it. So OpenHands Versa is now the default agent in OpenHands. All our code is open source, so you can go ahead and scrutinize the results, try out this agent. And like we also have another work on open agent safety where we actually evaluate the safety of OpenHands for workplace style environments and checking whether it's like doing something unsafe or not. And yeah, so that's pretty much it from my side. Happy to answer any questions.
Thank you so much for the great introduction to OpenHands and OpenHands Versa.